Hello everyone, welcome back. In this video, we're going to talk about crystallographic planes. In the previous sessions, we talked about point coordinates. We used point coordinate to find directions. We said point coordinate, it's location of an atom within the unit cell. Direction representing set of atoms on the same line. Now we will talk about planes. Now planes are similar to direction, but in a two-way. So in direction, if it's a one-way arrangement, plane will be two-way arrangement. Now let's show you. Now when we look at these atoms, we explain the location of them. We call point coordinates. Arrangement on one line, we call it direction. So if you look at it in a 2D, for example, this is gonna be plane of atoms. So you can talk about this two-dimensional. It's a plane of atoms. So this is one vector, two vector, direction, the third direction vector, the fourth direction vector, combined together in a two-dimension. It's going to give us plane. We have many more way of plane representing plane. For example, we can say, okay, this is a plane of atoms. Or make it larger in the dimension. It's 2D representation of atom arrangement within the crystal structure. Yeah, I'm representing in many crystal, but when we explain them, we represent them in a unit cell, which will be representing the main crystal structure. Now, in order to represent crystal structure, we're going to use three indices, HKL. For in the plane they call them Miller indices, HKL, and we use the round parenthesis here, or brackets. Remember, for direction we used square bracket. Square bracket represents direction, or normal bracket, or they call them parentheses, will be used for plane. Now again, we will divide this into two categories. When finding the Miller indices, HKL, and the second part is drawing the plane if we have the Miller indices. Now you see that those are, we call them a plane. Plane means a two-dimensional area which atoms will lie between or inside this plane, or you can say that it's passing through a set of plane in two dimension. Alright, let's start with easy thing, explain them how we find Miller indices first way. Then so dividing in two categories and how to find the Miller indices. This is HKL. Now in the first one we will have the plane. We're going to find HKL. The second one will be how to draw. How to draw plane there. Now let's have some plane or starting. Let's see. Let's talk about this plane first. When talk about plane, it's a two-dimensional so say it like this, a two-dimensional area. We have it, a two-dimensional area. So how do we represent this? How do you represent this plane in those Miller indices? We're going to talk about them. Now first, let's assume the direction of our axes. Let's say this is going to be the y-axis, and this is going to be, let's just have it here. So this is going to be the y-axis, this is x-axis, and this is z-axis. In order to represent a plane, we need to find HKL, Miller indices. Now, those Miller indices are related to the intersection of the plane with the axes. Now, you have to imagine this plane. It's like a paper, a sheet of paper. If you just bring it in front of your eyes, and you have to find the relation between this plane with the axis x, y, z. By relation, what do I mean? Is it parallel to the axis, or is it going to cut the axis somewhere? Now this rectangle, I have it here. Check the edge of the rectangle. This edge, let's use different color. This edge is parallel to y, yes? Since it's a rectangular, so this edge also is parallel to y. Now I need to find some information on this plane in order to find HKL. So if I check this plane, this edge and this edge parallel to y, so I know that this plane does not intersect with y at all. This is parallel to y. If I check the vertical side of the plane, this is parallel to z. This is parallel to z. So since the two edges are parallel to z here again, so we know that this plane does not intersect with z-axis. With z-axis. Now mathematically, what do we say? We'll say intersection with y at infinity. Mathematics says like this, yes? Intersection with z at infinity. You're not gonna reach to infinity. That's why they say intersection at infinity. So we represent the intersections with three letters: A, intersection with x-axis; B, intersection with y-axis; capital C, intersection with z-axis. Now we know that with y-axis, it intersect at infinity. And for C, which is z as well, intersection with z, it's at infinity. Since we know that it's not going to intersect, but we in mathematical we write intersection at infinity. Now remain intersection with x-axis. Intersection with x-axis. Remember, A, its intersection with x-axis, B representing intersection with y-axis, C representing intersection with z-axis. Since we know it's parallel to z, parallel to y, and it's parallel to z, so both of them, the intersection will be at infinity. Wow, we have intersection with x, yes. Now if you check the section, we know that it's going to intersect x somewhere here. This intersection we have it, yes. You check this an intersection with the plane with x. Intersection of the plane with x is at this point here. Now this point will be what for us? Will be what? We represent this as a fraction of the unit cell. Now this is the edge of the unit cell, yes. We call this one 1. We call this one 1 because at the corner, so we know that the intersection with x will be at 1. This one means at the corner because it's edge, yes, the edge of the unit cell, which will be the corner, full length of the edge. That's 1 means here. Now, this is what I mean by finding relation between the plane and the axes. We don't have intersection with y. I need you to imagine that there is a paper in front of your eyes and it's basically parallel to your face. If you put it straight, it will be parallel to your face in the y direction and z direction. For the x direction, for example, the way that you're holding it by your hand, it's intersecting with your hand, which you can represent it as the x-axis, which is going to be here. Now if your face is somewhere here, your face is here at the back, and this is going to be your hand here, which your hand, for example, holding the paper there. Now you know that the paper, it's vertical, it's parallel to your face in 2 directions, which is going to be x and y, y and z, but it's intersecting with your hand. Yes, your hand will be the x-axis. That's why you have 1 here, because intersecting with the x-axis. This will be clear when we explain in more examples. Now, how do we convert ABC to HKL? Well, we're taking reciprocal, or the inverse of them. So H is basically 1 over A, for K 1 over B, and for L 1 over C. Please do not mix this HKL with the direction indices. That's why our book, they use different letter for the direction. I mean the versions, the new version I have the book, they use HKL. I mean instead of HKL they use UVW in order to not mix them with the plane. But we know in direction how do you find HKL, and in the plane how do you find HKL. Remember, please do not mix between them. This HKL, the Miller indices for plane, we're finding like this: 1 over 1, that's going to be 1. Now 1 over infinity will be 0. If I anything by infinity will be 0 except infinity, and 1 over infinity again will be 0. So if you represent this plane, we represent in this manner. We'll say 1, 0, 0. This is how we represent plane Miller indices. First, we find the relation between the plane and the axes. I mean, by relation we mean the intersection. Is the plane going to intersect the axes? If they intersect, we need the value. If it does not intersect, which means parallel will be infinity. Now, let's solve another example here. images, no drawings. This will be a bit hard. Okay, at least it's clear that we have something cutting the three of them. Now, let's say we have a case like this, and there's a plane, we have it. Now let's say we have a plane. We put our axes, we put the axis here, put the axis here, put the axis here. We have some special cases, I'll come back to them later. Now let's say this is at the half, this at the half, this is will be the half, again half, putting all of them half here. That's a half alpha. Now, y-axis, x-axis, z-axis. Now this plane is a triangular plane. Triangular plane will not be parallel to any of the axes. This is one information that you will get it easily. Why? Because a triangular plane, there is no way that it can be parallel to any of the axes. It's going to cut the axes somewhere. So we're gonna go on finding ABC, then we'll convert them to HKL. ABC, intersection with x-axis, with y-axis, with z-axis. Remember, this is not going to be enough. You have to watch full video to understand, or at least the other videos to understand, because we have some cases that we cannot find the intersection easily. Now, ABC, intersection with x-axis, it's here, right here, intersection with x-axis, half, intersection with y-axis, half, intersection with z-axis, half. So, for triangular, it's easy, we'll cut the axis somewhere. Those values directly will be taken as the intercept values. So we have the intercept 1/2. When you're finding HKL, then we'll take 1/2. I mean, if you write it, because H is 1/A, 1/2, it's going to be 2, 1/2 for K2 again, and 1/2 for C, it's going to be 2. So the plane that we have it here, we represent in this manner, 2, 2, 2. Between parentheses, 2, 2, 2, which is the Miller indices for this plane. Now, let's represent another plane. I'm still doing simple. So we have a plane like this. Now this time I'm using 2. Let's see, not like this. Yes, let's do it here. I'm gonna represent something to you the same way that we did it in the direction. So let's have a plane like this. Now we have a plane like this. Let's assume this is the directions, the axes we have it here, x, y, z. sorry, let's keep it the same manner. This to be y, this to be x, this to be z. Now, intersection with y-axis, you know this plane is parallel to y-axis. So intersection with y-axis at infinity, because we know that this is parallel to y and it's parallel to z. We did in the beginning. The only difference we have it here is the intersection with x-axis. Now the intersection with x-axis is somewhere here, which is going to be 2 unit cell. So this is going to be 2. It's going to be 2. Now why I explain this one here, you will see it in a bit. Still the same in the first example we did. It was something like this, but in 1 unit cell. Now, if we're going to find HKL, H 1 over 2 remain as half. 1 over infinity will be 0. 1 over infinity will be 0. If you want me, will be 1 over 2. It's basically remain 1 over 2. I should write it in the beginning. And 1 over infinity, we know this is going to be 0. And 1 over infinity will be 0. Now, we are not allowed to leave indices in a fraction manner. So we have to multiply this one by a value that to get rid of these 2 at the bottom. So we multiply them by 2. We multiply by 2. In that case will be 1, 0, 0. Wow. Now if you go back to the beginning of the session, you realize that the one here we did in the beginning was exactly 1, 0, 0. 1, 0, 0. So what does that mean? What does that mean? We have equivalent planes. So no matter where is the origin, you will end up all of them they having the same indices. For example, this, 3 of them they have the same indices. Why? Because they call them equivalent planes. Equivalent planes that all of them they have the same indices. For example, if this is 0, 0, 1, this is the same thing, 0, 0, 1, 0, 0, 1. No matter where is the origin, no matter where you put the origin, you'll call them the same. So we call those equivalent plane. I mean, look, this is equivalent to this one, equivalent to this one. Now why? Because we explained that crystal structure is repeating itself. So if you have a set of plane like this, you would expect to have the same thing 1 block away. Look, 1 block away, you will expect having the same arrangement. And 1 block away, you're expecting to have similar arrangement. If inside here, there are, for example, let's say if this is BCC, if there's, for example, 5 atoms, you're expecting in the next block to have the same thing. Why? Because we said that crystal structure is repeating itself, so expecting this plane to have the same arrangement in a neighboring unit cell. So the same arrangement, 4 at the corner and 1 in the middle. The same thing as here, the same thing as here. And all of them represent them as the same thing. For example, if this is 1, 1, 0, there's also 1, 1, 0, this 1, 1, 0. I'll come back to this one. The same thing here, equivalent plane. Equivalent plane. So I did this one twice. In the beginning was only 1 cube, and it's 2 cube. I got exactly the same indices. Now, let's talk about the third type of now we might have Let's talk about this type of plane as well. Now let's assume that this is half. So let's assume that this is cutting at half. Here also is cutting at half. Now let's allocate the axis. We have it here. Remember, I'm still doing an easy things. Now this is y, x, z. This is a bit hard. It will be the hard. Let me just change the location of the origin. You all understand why I'm doing this one. Let me change the location of origin. I don't want to explain this one yet. Let's say this is the origin of location of origin will be here. You'll understand why we have to do this. Change of origin will be in the next video to explain that. Now let's say this is the origin we have it. This is the origin we have it. Well, we're going to find first intersection with x-axis, intersection with y-axis, intersection with z-axis. We call them capital A, capital B, capital C. Now, intersection with x-axis. Now this is x-axis and this is negative x-axis, yes? So this is basically here is the negative x-axis. Well, we have intersection there, yes? There is an intersection here. We have the plane intersect negative x-axis at 1 over 2. So it will be minus 1 over 2. The intersection with x-axis, this is x-axis positive, this will be x-axis negative. So it's intersecting with x-axis negative at half. So it will be 1 over 2 negative. Now intersection with y. Well, this edge is parallel to y. This is parallel to y. So we know that this plane is parallel to y. So intersection with y-axis is at infinity. You have to imagine this plane is parallel to y-axis. Look, this is going parallel to y. So it's infinity. Well, intersection with z-axis will be at the top of the cube. The top of the cube, which basically here, and top of the cube is 1. Top of the cube, I'm in the corner, so the top here, it's 1. Now converting it to the HKL, 1 over, let's write it down, 1 over minus 1 over 2, that's why it's going to be minus 2, and 1 over infinity here is going to be 0, and 1 over 1 here going to be 1. So representing this plane will be 2, 0, 1. 2, 0, 1. This is how we're finding HKL. Now, in order to understand the next video or next session, you have to understand that location of origin is very important. It's not something that you can decide anywhere by yourself. You cannot decide this origin anywhere of the corner. There is something here we have to understand, the location of the origin. It's not like coordinates, point coordinate or directions. In point coordinate, in direction, we said wherever you assume the location of origin, it doesn't matter. You will end up having exactly similar results. But for planes, the location of origin is very important. It's a specific points you have to choose. There are some possibilities, but not all of them will be possible. It's not like direction. We said you have 6 possibilities. Any corner you will place the origin, it doesn't matter. You will end up having exactly the same direction we showed to you with the videos. But for plane, we don't have this versatility of the location of origin, so we have to understand where to locate origin in order to find the Miller indices HKL, which we're going to explain in the next video.